Let's check out this common emitter circuit for how our tour book, doing our hand analysis that matches up with day number 2, the homework assignment, and also the what we're doing in lab. Here is the simulation version. First thing I want to show you is if you see this green in the bottom corner, this means that CircuitLab has actually solved the DC solution. You don't have to do any simulation. Go down to the simulation button. It already solved it. So if it can. If it's red, that just means there's some problem with it from there. All right, so we have, I'm probing up here. It says DC 2 volts. Of course it is. If I probe up here, it says DC plus 5 volts. Yeah, of course it is. And then down here it's 0. If I look at probe the emitter node with the collector resistor to be 1K, the emitter resistor to be 1K, it says DC 1.333 volts. That is a base to emitter voltage. If I subtract those two of, let's see, 0.666 repeating or 0.67 volts. For your hand calculations, you have been using 0.6 volts or 0.60 volts. This is a little different. Of course, it's a little different. You're using a transistor model that uses more precise and accurate models for this than the hand calculation model version, which just says it's 0.6 volts always. If I change this to something other and I go down to 1 volt, it resolves it. This is 1 volt. Now this is 0.366 volts or 366 millivolts. This is really great for playing around. If I want to change this over a larger range or many increments, this would get really tedious really quickly. This is where the simulation is useful. So we go to simulate here. I'm going to delete all of these from my last recording attempt. Add expression. Well, first of all, we can do this DC simulation. Really, we do these DC simulations all the time. CircuitLab does this already. I want a DC sweep. I want to vary the input from 0 up to 5 so I can see what happens. So I go here, click on this, we get a list. Where is this? VB. It's my source.V, that's the voltage. Linear, that's great. I want to go from 0 to 5, and at the moment we're going by 200 millivolts. We need some outputs, otherwise we don't get anything from here. Click on any wire or terminal. So I'm going to click on the base voltage, the collector voltage, the emitter voltage. We see V, parenthesis B, C, and E. That's great. You can actually type these directly, which is handy if you want to do a teeny bit of math. We'll see that in a minute. Run the DC sweep. All right, that's great. If you don't like the way the plot looks in CircuitLab, well, too bad. You can change it just a little bit, but it's not as configurable as you might like. But since it runs in the web browser, it's great. Let's look at the blue line. So the blue line, when the input is 0, blue is 0. When it goes up to 2 volts, blue is also 2. 4, 5. Do you notice how they track each other? I just plotted the input. So the input versus the input is a line with a slope of 1. Okay, not surprising. It's handy to see there, though, because it's also a transistor node that we're interested in. If I go back to 2, here's our 1.33 volts of the emitter voltage, the brown. And if you subtract 2 minus 1.33, that's our 0.67. You see that this 0.6-ish volts stays the same almost through this whole range. They don't get close together until the emitter voltage bottoms out at 0, which is our lowest voltage in the circuit, while the base voltage keeps going down and down and down. It kind of like pinches it. You notice that around 0.6 volts is when the emitter voltage starts to come off of 0. I want you to also notice at the same time up here at the collector voltage stays pegged at 5, and then right here it starts to come down and be very much a straight line. This is exactly, this is the simulation is doing what it does. But back here, if we go below a base voltage or a base emitter voltage below 0.6 volts, you see that the transistor just behaves differently. Below that, we're going to call this, for hand calculations, cutoff mode. If you do this specifically, or to figure out what mode this in at 0.4 volts, the emitter voltage is about 0 or 41 microvolts. So that PN junction between base to emitter, P to N, is forward biased. The PN junction from base to collector is reverse biased. That technically puts us into active mode, but we see that it behaves as if it's just shut off. There's no collector current, no voltage across the resistor. The collector voltage stays up at 5. So we call this cutoff. There's a little bit of fuzz or indeterminate right there. That's just where our model is less accurate. We keep increasing the input. Collector goes down. That's great. At this very crossover between orange and blue, and I don't have a data point there, I have it close, 2.8 volts at the input, the collector and the base voltage are equal. Well, that's a PN junction. Base to collector is P to N, and when it's 0 volts across that junction, we call that zero biased. It's neither forward biased nor reverse biased. It's just zero biased. There's no current flowing through that diode. It's like 0 volts across the resistor. It's just 0, nothing. Anything more than this, do you see how blue is now higher than orange? The base is higher than the collector. That means that PN junction between base and collector is forward biased. That is technically saturation mode because the base to emitter voltage has that PN junction forward biased also. So forward biased and forward biased, that's saturation mode. What I want you to pay attention though to is watch how the collector voltage drops very smoothly. Nothing, absolutely nothing radical happens at this crossover point. Besides, we go into a different mode technically. Nothing really happens in the shape until the collector and the emitter voltages really do get quite close together. I can't even see this in the plot because it puts the labels on top of each other. That happens at about 3.2 volts or so. If I want to see this curve a little better, I would simulate more data points. This looks a little jagged at this corner just because the plot is drawing straight lines in between places where there are no data points. When the input goes up more and more, now the collector voltage changes direction. That's really important. All the way from here and beyond, our transistor is in saturation mode. We're giving a command with the base to turn on. It is on all the way. We can't have that transistor be any more on than nearly a short circuit between the collector and the emitter. It's just pinched together, I guess. I would say pinched closed, but that sounds like an open circuit. It's really more like a short circuit. So that switch is on. Over here to the left, the switch is off. From here to the right, the switch is on. And in the middle, we have an amplifier. Let's look at the currents. I can add these expressions. If I hover on this, right on the transistor node, the base, I get the base current. If I delete the base voltage and the base current, and I click on exactly the base node of the transistor, you notice it gives me both the voltage, the node voltage, and the current. The current was there, or the voltage was there already, so it doesn't matter. Let's do this for the collector and the emitter. Notice this is the right at the symbol, and I get the base, collector, and emitter currents. Run that sweep again. We get two plots, and it's a little hard to see. Can I change these? I don't know what I'm doing. Okay. When we're at cutoff, all of our currents are 0. When we turn on, our currents start to go up. Collector current increases. Do you notice that the blue line right in the middle visually appears to be flat? Right where my cursor is at 2.2 volts, it says 10 microamps, 10.57 microamps. It's really small compared to the 1.5 milliamps of the other two. And that's active mode. The base current is, let's see, about 150 times smaller than the collector current. We would call that ratio beta. Right here at the saturation, we're not where we go into technical saturation, but when we go into effective saturation, this transistor is all the way on, our collector current stays positive, but it decreases, it changes direction. That inflection point is important to see. The base current starts to rise up and to be significant. One thing that's weird with this is this emitter current is way down here on the bottom. It's negative. What's up with that? We know when we look at this, the emitter current is labeled going out of the terminal. One thing that we want to be aware of is that in SPICE or in circuit simulators that are derived from SPICE, all currents related to a transistor are defined as positive going in. That's different than how we talk about them. So the base current is going in, collector current is going in. That's how we usually talk about them. But the emitter current is calculated as positive going in, but it's actually going out, hence it's negative. Well, I want to see it, the emitter current and the collector current, to be about equal, because we know they are. That's how the transistor is working. So what we do is we go over here to the iq1.ne, and I click on Edit. I go over to the beginning, and I make it negative. So I added a minus sign in front of this expression just by clicking Edit. I run the sweep again, and now you see brown is negative emitter current, but now it's the emitter current that we're thinking in our head. Collector current, in this whole range, emitter current and collector current are about the same. That's what fits with our hand calculation model. The base current stays very low. For our hand calculations, we just round it down to 0. As soon as we hit saturation mode, or actually effectively in saturation mode, the base current rises up, collector current decreases, stays positive. You notice the emitter current just keeps trucking right along, going up, which makes sense with your hand calculations that you've just done. I also want to point out that KCL is always true. The base current plus the collector current equals the emitter current. Isn't that great? All right, I think is that all I wanted to show? Yeah, that's all I wanted to show. Hey, thanks for watching.